So now we're using DNA-based markers. These are short tandem repeats or microsatellites. We use a standard panel of 12 microsatellites. The advantages to using the microsatellites, well, there are two basic ones. One is the people who gather the horses do not have to collect blood samples from horses that are not very anxious to donate blood samples. I've heard some good stories about what happens in the pens when they were trying to collect blood samples. But we can use pulled mane or tail hairs. We also can use some other types of tissues if necessary. And the DNA results are a little bit easier to obtain in the laboratory. The protein testing involved about 5 different techniques, whereas we run all of the microsatellites at the same time for each individual. So it simplifies the laboratory testing as well. The results were basically analyzed the same way as the blood proteins, but we changed the emphasis on some things due to the nature of the variability. So again, these are not as clear as they looked on my computer screen, but here is a particular HMA from Nevada. We calculated a lot of the same things, but we added some things this is just the mean number of alleles. This is the number of alleles with a frequency less than 5% in the population, or rare alleles, and this is a percentage of rare alleles. Using microsatellites, we put more emphasis on the allelic diversity because of the nature of the variation. Microsatellites have a high number of alleles, and so heterozygosity can be maintained at a high level even though diversity is being lost at the allelic level. And so it's important that you pay more attention to these values over here rather than the heterozygosity, but we do look at all of it. And again, we can do the look at relationships with the microsatellites. This is showing a larger set of breeds. This is because we're tending to report the entire tree now, whereas many times in the past we would just pick out a particular branch, say that if the feral horse came out in here, which is where this one does, these are the North American derived breeds. We might just show this area just for simplicity of the tree. And yeah, I was afraid this wouldn't come out. We have a little bit of problem with this particular thing. We're working on improving our graphics on this. This is showing a group of Nevada herds in a dendrogram, and there's about 60 some odd herds in that particular dendrogram, so it's very faint. So DNA loci give higher heterozygosity values simply because of the nature of the variability. That makes it difficult to compare the results that we got with the blood proteins directly. So we might have tested a herd with blood proteins and got 40% heterozygosity. If we tested it with the DNA, it might be 70%. What we do see is that the rank levels of variation are very similar, although not necessarily exactly the same. Of course, these are often not the same samples. So allelic diversity measures are more important for the microsatellite loci than they were for the protein loci. However, the DNA data is just as useful for population genetic analysis as the protein data, and now we're finding that there are actually more things we can do because there are lots of new statistical analysis that are actually tailored for more for the DNA variation, for the microsatellite variation, than for the protein data. And it's just simply progress in science in the way to analyze the data. So we tested somewhere around 100 populations using the blood proteins from the BLM. Some of these were tested more than one time, so it's not 100 distinct HMAs, but it was 100 individual sampling periods. During the period of transition, where we were doing our testing from proteins to DNA, we actually tested all of the herds that we got, with a couple of exceptions, with both sets of loci. So those we can compare directly because it's the same individuals getting the same thing. I'm currently in the process of looking at some of that information to kind of give us a better way of converting, understanding what the differences are. We have DNA data for approximately 180 sampling periods. So Dean said there's 179 HMAs. We haven't quite tested all of them yet. That's true, but we still have tested just about that many. Some of the herds we have tested, again, multiple times. Some herds we tested 3 times. I think one herd we tested 4 times, and that's the Prior Mountain herd, which was one of the very first ones we did back in 1991. We also test burros. It's basically the same testing protocol. We use the same set of markers to test them, but not all of them amplify the burro DNA or are not variable in the burros. One of the things that is different is that we do not have a great diversity of domestic breeds of burros. People don't breed burros the same way they breed horses, and they have just begun to treat burros the way they treat horses, which they, in recent decades, have begun to treat the way people treat dogs, and that is to breed them very closely, set breed registries and standards and all of that. That's a relatively recent development. So burros are more like horses were 100 to 150 years ago in terms of their domestic population structure. One of the things we are able to do, though, is we are able to make a comparative analysis of the domestic burros to the feral burros. And one of the things we're seeing is that most of the burro herds show very low variability. Many of them are showing levels of variability that are quite low. And I didn't pick one of those out for this particular slide, but you can see that the domestic mean is about 54% heterozygosity, whereas we're looking for these 3 burro herds at about 44% on average. And it's actually not uncommon to see burro herds with only about 20% variability. I got a focus issue there, actually. I wasn't sure if that was my eyes.
How many of those horse loci work on the burros?
Of the 12 that we routinely use, 9 of them. Yes. And we actually use a panel on the horses now, although we're not doing it for the BLM testing, but for our research into breed relationships and domestication and such. We're actually using a panel of 15. Before our burro testing, we add those additional 3, all of which do amplify. So, and some people have actually reported acceptable results on the burros for at least 2 of the 3 that we don't get to work, but we just haven't spent the time to see why they're not working for us. So again, the burros, I think, have in many cases had more severe population contractions probably more inbreeding because of smaller numbers on the land. And so I think the burros, in terms of genetic diversity, are a much bigger problem than the horses are. And again, we've tested a fair number of burros. I think this is all of them we had tested up until last year. And we are getting some more domestic populations for that. Since the last burros we have analyzed, we actually do have some more domestic burros to put into the comparison. So the basic summary is that for horses, the majority of the feral herds that are under BLM management have moderate to high genetic variability. By moderate, I mean something around the mean for the feral herds. Those values are very similar for the DNA. The means for the feral herds are very, very similar to the domestic means. This is predominantly due to the fact that these herds come from diverse backgrounds. It's not like one particular group brought out a herd of horses of one particular breed or family relationships, let them go, they grew up, expanded in numbers, and have been isolated. Most of the herds are of mixed ancestry, so they have high diversity, and in many cases, again, as Dean pointed out, they probably are exchanging genes between other HMAs in the wild. Sometimes we can detect that, sometimes we can see it, other times it's not so clear, and it's more difficult because of the high mixed ancestry of most of these populations.